Saturn's serene beauty hides a universe of secrets. That iconic globe with its perfect rings is a cosmic puzzle box, and for decades, its mysteries have defied every explanation. By the end of this journey, you will have explored 25 of its most baffling enigmas. We will confront a permanent hexagonal storm large enough to swallow Earth and investigate the ghostly shadows that race across the rings. What force could possibly maintain a perfect geometric shape in a raging gas giant's atmosphere? Which of Saturn's secrets do you find the most compelling? Circling Saturn's North Pole is a structure so strange it seems to defy the laws of physics. This is the Hexagon, a colossal six-sided jet stream that has raged for at least 4 decades, a permanent geometric storm etched onto the face of a gas giant. The Voyager probes first glimpsed its angular shadow in the 1980s, but it was the Cassini mission that revealed its full, staggering majesty. Each side is wider than our entire planet, a honeycomb pattern of winds moving at hurricane speeds, yet locked into a shape of perfect symmetry. How can a fluid, chaotic atmosphere produce and maintain such a rigid, geometric form? It is a puzzle that has spawned numerous theories. Some scientists propose it is a colossal standing wave pattern, a stable ripple in the atmosphere's fabric. Others suggest the answer lies deep within Saturn, in complex interactions between different layers of its churning interior. While hurricanes on Earth form and dissipate, this hexagon is a permanent fixture, a celestial landmark unlike anything else we have observed in our solar system. The very fact of its existence challenges our fundamental understanding of planetary weather. But that geometric storm is not the only artist at work on Saturn. High above the polar hexagon, the planet's magnificent rings hold a mystery of their own, one that appears and vanishes like a phantom. These are the spokes, fleeting dark and bright streaks that stretch radially across the vast B-ring, resembling the ghostly spokes of a spinning wheel. They materialize, rotate for a few hours, and then simply fade away, a transient performance on a cosmic stage. The Voyager spacecraft first captured these enigmatic features, and for a time, scientists believed they were a seasonal quirk. Yet Cassini witnessed them too, confirming they are a persistent, if elusive, phenomenon. Their behavior is utterly bizarre, for they do not orbit in step with the ring particles. Instead, they seem to be locked to the planet's powerful magnetic field, rotating at a different speed entirely. So what could create these colossal, temporary scars across the rings? The leading theory points to electrostatic forces. Picture a cloud of tiny, fine dust particles hovering just above the denser ring material. If these minute particles become electrically charged, perhaps by solar radiation or plasma in Saturn's magnetosphere, they could levitate, casting slender shadows that appear as dark spokes from afar. Bright spokes might be the same phenomenon viewed from a different angle, where sunlight scatters off the elevated dust. This idea elegantly links the spokes to Saturn's magnetic personality, but crucial pieces of the puzzle are still missing. Scientists cannot yet fully explain the precise trigger for their formation or predict their fleeting appearances. Why do they come and go with such ghostly irregularity? The spokes are a haunting reminder that even Saturn's most iconic features are not yet fully understood. Beyond these fleeting patterns lies a question that strikes at the very identity of Saturn itself. Are its glorious rings a permanent feature of the solar system, or are we witnessing a temporary cosmic spectacle? The age of Saturn's rings is one of the most profound debates in planetary science, with Cassini's final data delivering a shocking verdict. For a long time, it seemed natural to assume the rings were as ancient as the planet, primordial leftovers from the disk of dust and ice that formed the solar system over 4 billion years ago. Yet, close measurements of the ring's mass and composition told a different, more startling story. Cassini revealed the rings are far too clean and bright. If they were truly ancient, they should have been darkened and polluted over billions of years by a constant rain of meteoroid dust, their pristine ice stained a deep, murky brown. Their astonishing brightness suggests they have not endured that cosmic pollution for very long. Furthermore, precise measurements of their total mass showed they are surprisingly lightweight. This critical piece of evidence points toward a younger age. A more massive ring system would better resist the relentless forces that pull material inward and spray it out into space, processes that would erode a lighter system on a cosmically short timescale. The accumulating evidence now suggests Saturn's magnificent rings could be as young as only 100 or 200 million years old. This is a blink of an eye in cosmic terms, meaning they did not exist when dinosaurs roamed the Earth. They may have formed when a stray icy moon wandered too close to Saturn and was torn apart by the planet's immense gravity. This theory forces us to completely reconsider our solar system's history. We are not looking at an ancient relic, but a dynamic, evolving structure that may one day, millions of years from now, fade from view entirely. This beautiful, temporary structure is actively vanishing before our very eyes. Cassini's final, daring orbits between Saturn and its rings uncovered a startling phenomenon, a celestial downpour known as ring rain. The spacecraft detected a torrent of icy particles, primarily from the inner D-ring, cascading down into the planet's upper atmosphere. This is not a gentle drizzle but a deluge, with estimates suggesting it carries enough water to fill an Olympic-sized swimming pool from the rings every single day. This constant erosion is sculpting the rings and stealing their substance, pulling them into a slow but inevitable decline. The implications are staggering. This ring rain provides a direct mechanism for the rings' eventual demise. The same data that suggested the rings are young also paints a picture of their future. Projecting this loss rate forward, scientists predict the rings could be completely gone in just another 100 million years. We are living in a remarkably special era, a narrow window in cosmic time where Saturn wears its glorious crown. So why are we here to see it? The odds seem almost impossibly fortunate. It forces us to confront a profound question of cosmic timing. Is our existence coinciding with this ephemeral display just a lucky accident, or does it tell us something deeper about the dynamic, ever-changing nature of planetary systems? We are witnessing a fleeting masterpiece, a celestial spectacle with a definite expiration date. This stark division between creation and destruction finds a perfect mirror in one of Saturn's strangest moons. Iapetus presents a face of pure cosmic contradiction, a world split directly in half. One hemisphere shines with the brilliance of freshly fallen snow, while the other is stained a deep, dusty charcoal. From a distance, it looks like a celestial yin and yang, a perfect balance of light and dark locked in its orbit. The mystery of this two-faced moon has captivated astronomers for centuries, and the closer we look, the stranger it becomes. The leading explanation is as elegant as it is bizarre, a process called runaway thermal migration. Here is how it might work. Imagine a thin layer of dark, dusty material settling on one side of the moon. Because this dark material is so effective at absorbing sunlight, it grows warm. This warmth then heats the underlying water ice, causing it to turn directly from a solid into a gas, a process known as sublimation. This water vapor then travels across the moon and refreezes on the colder, brighter areas, making them even whiter and more reflective. This, in turn, leaves the dark areas even darker and more exposed, allowing them to absorb even more heat, which sublimes even more ice. It is a self-reinforcing cycle, a feedback loop that over millions of years could have exaggerated a slight initial stain into the dramatic, absolute division we see today. But this elegant theory immediately raises another, deeper question. Where did that initial dark material come place? What was the original paint that started this entire process? Some scientists point to Phoebe, another of Saturn's distant dark moons. They suggest that fine dust ejected from Phoebe by micrometeorite impacts could have drifted inward, slowly coating the leading hemisphere of Iapetus as it plows through this cosmic debris field. Yet, the composition of the dark material on Iapetus does not perfectly match what we see on Phoebe, leaving room for other ideas, such as the possibility that the dark stain emerged from within Iapetus itself. The Moon itself may be somehow bleeding this dark material onto its own surface, so we are left with a dual mystery, not just how the two-faced appearance works, but what substance set this incredible transformation in motion to begin with. While one moon presents a puzzle of dark and light, another holds a secret ocean. Enceladus, a small, icy world no larger than the British Isles, was once thought to be a frozen, geologically dead relic. Then the Cassini spacecraft witnessed the impossible. Plumes of water vapor and ice crystals were erupting from massive fractures at its south pole, shooting hundreds of miles into space. These are not mere puffs of gas, but colossal geysers powered by a vast global ocean of liquid water hidden beneath the Moon's frozen crust. The evidence for this subsurface sea is overwhelming. Cassini did not just photograph the plumes, it flew directly through them, tasting their contents. The spacecraft's instruments detected salt, silica nanoparticles, and a surprising cocktail of organic molecules, the carbon-based building blocks essential for life as we know it. Here, in the frozen outer reaches of our solar system, a tiny moon was offering up the ingredients for a biological recipe, but such a distant ocean sealed under a shell of ice should be frozen solid. What immense force could keep it liquid and power these spectacular eruptions? The leading suspect is tidal heating. As Enceladus travels along its slightly elliptical orbit around Saturn, the planet's immense gravity constantly squeezes and stretches the Moon. This relentless flexing generates immense internal friction and heat, acting like a cosmic engine that prevents the ocean from freezing and fuels the geysers. The silica particles found in the plumes suggest that this hot water is interacting with a rocky core on the ocean floor, at temperatures that could be similar to those around hydrothermal vents in Earth's deepest oceans. These vents on our own planet are teeming with life, thriving in complete isolation from the sun's energy. This single fact transforms Enceladus from a curious moon into one of the most promising places in our entire solar system to search for extraterrestrial life. The profound, ongoing mystery is not just what lives in that dark abyss, but what specific, powerful energy source deep within this small world drives such a persistent and vibrant display. Yet even that hidden ocean seems orderly compared to the cosmic wreck orbiting nearby. Hyperion is a moon that defies every expectation of a solid world. It looks less like a celestial body and more like a colossal piece of cosmic pumice, a porous sponge floating in the void. Its surface is a nightmare landscape of deep, dark craters with razor-sharp edges, giving it an unsettling, fractured appearance unlike anything else we have seen. But its bizarre look is only the beginning of the mystery. The true enigma lies in what it is made of. Hyperion is incredibly light, with a density so low that it must be mostly empty space. Scientists estimate this moon is about 40% hollow, a fragile web of ice and rock barely holding itself together. If you could find an ocean large enough to place it in, Hyperion would actually float. This extraordinary porosity is the key to its survival. When other objects strike it, they do not create ejecta or smooth craters. Instead, they simply compress the material like punching a block of foam, leaving deep, scarred pits that never heal. This sponge-like quality absorbs impacts, preventing the moon from being shattered apart over the eons. But this leads to a baffling question. How did such a fragile object even form? It seems too delicate to have survived the violent early solar system. One compelling theory suggests Hyperion is the largest remaining piece of a much larger moon that was utterly shattered by a catastrophic impact long ago. The debris from that collision, instead of coalescing into a new, solid sphere, simply clumped together into this loose, porous aggregate, a celestial ghost of a destroyed world. Adding to its strangeness is its complete lack of control. Hyperion tumbles through its orbit in a state of pure chaos. It does not rotate predictably like Earth or even slowly like our Moon. Its axis of spin wobbles so violently and unpredictably that it is impossible to know which part of its surface will face Saturn from one day to the next. This chaotic rotation is likely due to its irregular shape and the gravitational pushes and pulls from its neighbor Titan. So we are left with a moon that is both a survivor and a wreck, a fragile, spinning enigma that challenges our very ideas of how moons are built and endure. What other secrets are locked within its porous, shadowy chambers? While one moon hides a water ocean, another flaunts a landscape hauntingly familiar. Titan, Saturn's largest moon, is a world with its own alien hydrologic cycle, a mirror of Earth painted with entirely different materials. It is the only moon in our solar system with a substantial atmosphere, a thick orange haze that shrouds its surface in mystery. Beneath that smog, radar has revealed a stunning geography of rolling dunes, great lakes, and winding river valleys, but these are not carved by water. On this frigid world, the role of water is played by liquid methane and ethane. Titan has rain, clouds, rivers, and seas, all flowing with hydrocarbons. This creates an active, complex weather system that erodes its surface and fills its basins, a dynamic world that feels strangely alive. Yet this entire magnificent cycle is built on a foundation of mystery. The sun's ultraviolet radiation relentlessly attacks methane in Titan's upper atmosphere, breaking the molecules apart. This destructive process should have consumed all of the moon's methane, turning its lakes to dust and its skies clear within a few tens of millions of years. Titan is billions of years old, so its methane is somehow being constantly replenished. The question is, from where? What hidden reservoir is feeding this alien weather? One possibility is a vast subsurface ocean of liquid water, much like the one on Enceladus, which could be releasing methane through vents or cracks in the icy crust. Another theory suggests a deep reservoir of methane stored within Titan's icy mantle, slowly seeping out to the surface over eons. Or perhaps the source is even more exotic, a layer of methane-rich clathrates, icy cages that trap the gas, acting as a global storage tank that slowly leaks its contents. Each explanation presents its own challenges, and the true source remains one of Titan's most profound secrets. This ongoing cycle of destruction and renewal makes Titan a world in a delicate balance, a place where the very substance of its rivers and lakes is locked in a constant, invisible struggle for survival against the harshness of space. Even Titan's complex atmosphere cannot obscure a more fundamental mystery, one that lies at the very heart of Saturn itself. We cannot say with certainty how long its day is. Determining the rotation rate of a gas giant seems like it should be a simple task, but Saturn has proven to be a master of deception, giving different answers depending on how you ask the question. When scientists track cloud movements in its atmosphere, they get one rotation period. When they measure the pulse of its magnetic field, they get a completely different and much slower rhythm. This discrepancy is more than a mere technical glitch. It is a profound clue about the hidden nature of the planet. The magnetic field measurement was long considered the gold standard, the true heartbeat of a planet, because a magnetic field is generated deep within a planet's churning metallic core. On Jupiter, this method works perfectly, giving a clear and consistent rotation period. But Saturn's magnetic field is bizarrely symmetrical, almost perfectly aligned with its axis of spin. It lacks the telltale wobble that spacecraft can use to clock the rotation of the deep interior. This strange symmetry means there is no obvious magnetic pulse to track. The best estimates from the Cassini mission, taken during its final, daring dives, suggested a deep rotation period of about 10 hours and 33 minutes. Yet, if you watch the cloud tops, they complete a lap roughly 5 or 6 minutes faster. So which one is the true length of Saturn's day? The answer may be that both are correct in their own way, revealing a planet at war with itself. The leading theory is that something remarkable is happening in Saturn's outer layers. Swirling rivers of electrically conductive fluid, perhaps helium rain falling through a sea of liquid metallic hydrogen, could be dragging the magnetic field along with them. This would slow down the magnetic field's apparent rotation compared to the solid core deep below. Essentially, the planet's magnetic heartbeat is being smeared across thousands of miles of its interior. This creates a fundamental disconnect between the spin of the outer envelope we can see and the spin of the hidden heart we cannot. The very nature of Saturn's deep rotation remains one of the most basic yet elusive facts about it. How can we truly understand a world when we cannot even measure its day? While Saturn's deep rotation remains a puzzle, its polar regions hold a thermal anomaly just as baffling. High above the South Pole, scientists discovered a colossal zone of intense heat, a warm polar vortex completely defying expectations. This is not a gentle warming, but a massive hotspot trapped inside a hurricane-like eye wall over 5,000 miles across. The eye of this polar storm is dramatically warmer than its surroundings, a blistering island in a part of the planet that should be one of the coldest. On Earth, our poles are frigid, receiving less sunlight and radiating their heat into space. Saturn, so much farther from the Sun, should exhibit this effect even more extremely. Yet this vortex is a persistent oven, a source of heat that has no obvious explanation. So what mysterious engine is driving this thermal powerhouse? The source of the heat is the core of the mystery. Some scientists theorize it is linked to Saturn's powerful auroras. Just like Earth's northern and southern lights, Saturn generates spectacular light shows near its poles as charged particles from the Sun spiral down its magnetic field lines and collide with the atmosphere. These collisions deposit immense energy, potentially heating the thin, upper air and creating a high-altitude hotspot. But does this account for the sheer scale and intensity of the warmth observed deep within the vortex? The intricate dynamics of this system are still not fully understood. The swirling winds of the vortex itself may act like a giant atmospheric lid, effectively trapping this heat and preventing it from dissipating into the surrounding environment. This creates a self-contained thermal prison, a persistent pocket of warm air that churns endlessly over the pole. It is a stark reminder that the energy balance of a gas giant is far more complex than we once imagined, governed by a combination of external bombardment from the Sun and internal processes we are only beginning to grasp. What other hidden sources of energy are churning within Saturn's depths waiting to be discovered? Yet the rings hold structures even stranger than the spokes. Etched into the bright bands of the ring are thousands of peculiar features known as propellers. These are not solid moons, but ghostly imprints, S-shaped disturbances that stretch for miles yet are so small they push the limits of what our cameras can resolve. Each propeller is the gravitational signature of an unseen architect, a tiny, embedded moonlet likely no larger than a kilometer across. This miniature world is constantly at war with the very ring it inhabits. Its gravity is strong enough to pull the fine ring particles around it, clearing two partial, empty lanes on either side of its orbit. But it is not powerful enough to open a full, clean gap like the ones carved by larger moons such as Pan or Daphne's. The result is this dual scar, a celestial wake that looks exactly like a two-bladed airplane propeller frozen in the ice. The existence of these propellers reveals a hidden population of tiny moons, a whole class of objects we never knew existed. And their survival is a profound puzzle. According to our models, these small moonlets should not last long. The relentless pull of Saturn's gravity and the constant bombardment from surrounding ring particles should either shatter them or drag them down into the planet on a very short timescale. Their very presence suggests they are constantly being replenished, or that they possess some unknown property making them far more resilient than we thought. Perhaps they are not solid, monolithic rocks, but loose, fluffy aggregates of material, cosmic dust bunnies whose porous structure allows them to absorb impacts without being destroyed. How do these tiny architects endure within the chaotic traffic of the rings, and what does their stubborn existence tell us about the birth and continual rebirth of Saturn's most stunning feature? Even the tiniest architects in Saturn's rings can shape worlds of profound strangeness. Circling within the very gaps they help maintain are two of the most peculiar moons ever discovered, Pan and Atlas. Their shapes defy simple classification, looking less like spheres and more like delicate cosmic ravioli or flying saucers. Each possesses a startlingly thin equatorial ridge, a bulging belt of material that gives them an almost sculpted appearance. How does a moon end up looking like a piece of pasta? The answer seems to lie in their unique location, embedded within Saturn's ring system itself. These small moons are the shepherds of their gaps, their gravity clearing a path through the icy particles. But that same gravity also draws in the very material they are pushing away. Scientists theorize that over millions of years, fine dust and ice from the rings have gently settled onto these moons. Because they spin, this material does not coat them evenly. Instead, it preferentially accumulates around their equators, much like a spinning ball of dough would gather flour along its widest point, slowly building up that distinctive, sharp ridge. This process of slow, gentle accretion from their immediate environment is what likely forged their bizarre forms. Yet this explanation immediately raises another question. Why do only some moons look like this? Other small moons, like Prometheus and Pandora, also interact with the rings but remain more potato-shaped. The secret may be a delicate balance of forces. Pan and Atlas orbit very close to the rings within a dense plane of fine material perfect for accretion. Their gravity is also just right, strong enough to pull in particles, but not so strong that it would disrupt the gentle settling process. Their slow rotation rates likely play a role too, allowing the material to pile up gradually rather than being flung away. They exist in a perfect sweet spot where the environment provides a constant supply of construction material and their own physical properties allow them to wear it like a belt. This transforms them from mere moons into active geological records. Their strange shapes a direct diary of their long-term relationship with the rings. They are not static objects, but worlds still being built one dust particle at a time by the very system they help govern. What other strange forms might be hiding in the rings, still too small for our cameras to see? This profound tilt, a dramatic lean of over 26 degrees, gives Saturn its spectacular seasons and defines the angle from which we view its rings. Yet such a sharp axial slant is itself a cosmic mystery. Why is this giant world so dramatically knocked over? The leading explanation involves a gravitational dance of almost unimaginable duration and subtlety, a slow-motion tug of war with the planet Neptune. This theory, known as the resonance model, suggests that Saturn's own migration through the early solar system locked it into a rhythmic relationship with its distant blue neighbor. As both planets drifted outward from the Sun over billions of years, the timing of their orbits may have synchronized. For every 2 orbits Saturn completed around the Sun, Neptune may have completed 1. This precise 1-to-2 resonance creates a powerful and cumulative gravitational nudge. With each synchronized pass, Neptune's pull would have ever so slightly tugged on Saturn, gradually pulling the entire planet over onto its side, like a top being slowly toppled by an invisible finger. This grand model of planetary migration elegantly explains the tilt, but it is not without its complications. The intricate orbital choreography required is incredibly delicate. For this process to work, Saturn must have migrated at just the right speed and at just the right time, a series of events that some newer simulations struggle to replicate perfectly. This has led scientists to consider alternative ideas. Perhaps the tilt was not caused by an external force at all, but by an internal one. Could a massive impact in the solar system's violent youth have delivered enough angular momentum to knock Saturn askew? Or is the answer even more complex, involving gravitational interactions not just with Neptune, but with Jupiter and Uranus as well, a chaotic ballet of giants that left each one with its unique posture? The true story of Saturn's lean is likely written in the faint gravitational scars of that ancient migration, a puzzle that challenges our very understanding of how the solar system settled into its current, seemingly stable arrangement. This delicate celestial structure is a ring that should not exist. The G-ring is one of Saturn's faintest and most isolated bands, a tenuous loop of dust and ice lying far beyond the planet's main ring system. For years, its very presence was a puzzle. Unlike the brilliant main rings, which contain immense amounts of material, the G-ring is incredibly sparse and faint. Simple orbital mechanics dictate that such a diffuse ring should have dissipated and vanished long ago, its particles scattered by solar radiation and gravitational tugs. The ring was clearly being actively fed, but the source of that material remained a ghost. The mystery was solved only when the Cassini spacecraft, with its sharp-eyed cameras, finally spotted the culprit. Hidden within the ring's bright inner edge is a tiny, secret moonlet named Iapetus. This minuscule world is barely a kilometer across, a mere speck of rock and ice that is the hidden heart of the entire G-ring. Iapetus is the source, the tiny architect of this faint, ethereal band, but its discovery only deepened the mystery. How could such a small object possibly sustain an entire ring? The leading theory is a process of cosmic erosion. Iapetus is under constant bombardment by micrometeoroids, tiny grains of space dust traveling at incredible speeds. Each microscopic impact blasts a tiny puff of dusty debris off the moonlet's surface, launching it into orbit around Saturn. This steady stream of ejecta acts like a celestial conveyor belt, constantly repainting the G-ring with fresh material, replacing the particles that are inevitably lost to space. Yet this elegant explanation is not the full story. The process is far more complex than it first appears. Scientists cannot yet fully model the delicate balance at play. The ring's stability depends on a perfect, ongoing equilibrium between the rate of debris creation and the rate of its dispersal. The impacts must be frequent enough to offset the losses, but not so violent that they shatter the tiny moonlet completely. What specific properties of Iapetus' surface and composition allow it to withstand this relentless sandblasting for millions of years? Is its structure unusually fluffy, absorbing impacts without fragmenting, or is it a solid rock that simply sheds its dust coating over and over again? The G-ring and its secret moonlet represent a perfectly balanced, yet poorly understood cosmic system, a fragile dance of destruction and creation happening in the silence of space. Deep within the swirling gases of Saturn's upper atmosphere, a fundamental ingredient has gone missing. Planetary scientists have found a surprisingly low amount of ammonia, a chemical they expected to be abundant. Based on our understanding of how the solar system formed, Saturn should be rich in this compound, yet its outer layers tell a different story. It is as if someone has been secretly siphoning it away. So where has all the ammonia gone? One compelling hypothesis paints a dramatic picture of alien weather. It suggests that ammonia is being effectively hidden from view, not because it is absent, but because it has been dragged down into the planet's deeper, hidden layers. The proposed mechanism is a form of colossal precipitation. In the cold, high-pressure environment of Saturn's atmosphere, ammonia can dissolve into water droplets, creating a slushy mixture of water and ammonia. This mixture can then freeze into what scientists call ammonia water hailstones. Imagine a storm on a scale we can barely comprehend, where chunks of this exotic ice, some as large as golf balls or even bigger, form in the upper clouds. But unlike hail on Earth that eventually falls to the ground, these hailstones are far denser than the surrounding hydrogen-helium atmosphere, so they begin a long, slow, and permanent descent. They plummet downward for thousands of miles, acting like tiny freight trains, transporting their cargo of ammonia deep into the interior, far beyond the reach of our telescopes and probes. This process, known as sequestration, would effectively scrub the upper atmosphere of its ammonia, leaving behind the curiously depleted levels we observe. This theory elegantly explains the missing ammonia, but it also reveals a world of incredible dynamism beneath the cloud tops. It suggests that Saturn's interior is not a uniform soup, but a place of active, layered chemistry and colossal weather patterns, where exotic forms of rain and hail continuously reshape the planet's chemical makeup from the inside out. What other common substances might be hiding in the depths, pulled down by similar celestial storms we cannot even see? While the outer rings appear majestic and serene, the innermost band tells a story of constant, rapid change. This is the D-ring, a faint and dusty halo clinging close to Saturn's cloud tops, and it is by far the most dynamic and restless part of the entire ring system. Unlike the more stable rings farther out, the D-ring is a place of transient structures and ripples that shift over timescales we can actually observe, from weeks to mere months. It is a ring in motion, and its behavior defies the ancient, placid image we often have of Saturn's jewelry. One of the most startling discoveries was a set of ripples that raced through the D-ring like waves across a pond. These were not random patterns, but organized spiral corrugations expanding outward. The speed of their movement was the key to unlocking their origin. Scientists traced these ripples back in time, and the calculation led to a single dramatic event in 1983. A cloud of cometary debris, perhaps the remains of a shattered comet, is thought to have slammed into the rings. The impact tilted a vast sheet of ring material slightly out of its original plane. Over the decades that followed, Saturn's gravity worked on this tilted sheet, winding it up into the tight, spiraling ripples that Cassini eventually observed. This means the D-ring holds a fossil record of a specific cosmic collision, a ghostly echo of an event that occurred decades before we even knew to look for it. But cometary impacts are not the only force at work here. The D-ring also exhibits strange, rotating structures that appear linked to the planet's powerful magnetic field. Just as the spokes in the B-ring seem tied to Saturn's rotation, certain features in the D-ring may be shaped by invisible electromagnetic forces. Charged particles trapped in the magnetic field could be interacting with the fine dust of the D-ring, pushing it into new configurations as the planet spins. This creates a ring that is not just responding to gravity, but is also a visible tracer for the complex and invisible magnetic dances happening around the planet. The D-ring's faintness and constant activity raise a profound question. Are we witnessing a ring in its final death throes, or is it a ring in the process of being born? Its proximity to Saturn means it is subjected to the strongest gravitational and magnetic stresses, which could be tearing it apart. Yet, it could also be a place where material is constantly being replenished, perhaps from micro-impacts on the inner moons or from particles spiraling down from the brighter rings above. This innermost band is a cosmic laboratory of change, a place where the forces that create and destroy planetary rings are playing out in fast forward right before our eyes. What other fleeting patterns will we discover there before it vanishes for good? This delicate celestial architecture requires a pair of meticulous gardeners. Pandora and Prometheus, two small, potato-shaped moons, perform an intricate gravitational ballet around Saturn's narrow F-ring. Their task is one of cosmic precision, to confine the ring's countless icy particles, preventing them from either drifting apart into the void or collapsing inward. These are the shepherding moons, and their constant, slight gravitational tugs sculpt the ring into a stunning display of dynamic chaos. As they pass by, their gravity pulls and pushes at the ring material, carving temporary channels, braids, and bright streamers that look like cosmic kite tails. It is a ring that is constantly being woven and rewoven by its celestial guardians, yet this beautiful dance is far from stable. The orbits of Pandora and Prometheus are themselves slightly chaotic, their paths shifting over time in a way that should, according to our models, lead to disaster. Their gravitational influence is so delicate that even a tiny miscalculation could cause one of them to either plunge through the ring, scattering it forever, or to lock into a destructive resonance with the other. The profound mystery is how this system has maintained its apparent stability for so long. How do these two moons avoid the gravitational pitfalls that should have torn this fragile ring apart eons ago? One theory suggests that their chaotic orbits are actually the key to their success. Instead of settling into a perfectly predictable rhythm, their slight orbital wobbles might prevent them from ever applying a consistent, disruptive force to the same section of the ring over and over again. Their chaos could be a form of stability, a way of ensuring that their sculpting effects remain temporary and self-correcting. Another possibility is that the F-ring itself is not as fragile as it appears. Perhaps it is constantly being replenished by unseen source moons, or its particles have just the right balance of stickiness and elasticity to withstand the shepherd's persistent poking and prodding. The survival of this narrow, braided ring is a testament to a gravitational balancing act of astonishing complexity, a system that continues to defy our predictions of cosmic order. Saturn's gravitational embrace holds another world of contradictions, a moon whose appearance tells one story while its hidden nature whispers another. This is Mimas, often called the Death Star moon for its single, colossal crater that gives it an uncanny resemblance to that fictional battle station. That giant impact scar, named Herschel, is so vast it nearly shattered the moon, a permanent reminder of a violent past. Yet the true mystery of Mimas is not written on its frozen, cratered surface but locked deep within. Mimas is profoundly lightweight, with a density so low it must be composed almost entirely of water ice. It is essentially a giant cosmic snowball. This simple fact creates a baffling puzzle. If Mimas is just a loose pile of ice and rubble, how did it survive the Herschel impact, an event that should have blown such a fragile world to pieces? The sheer rigidity of its surface, holding that massive crater basin, suggests a structure far more solid and cohesive than a simple ball of slush. So what is holding this icy moon together? One radical possibility is that Mimas, like its neighbor Enceladus, hides a secret ocean of liquid water. This is a deeply counterintuitive idea. Mimas shows no outward signs of geologic activity. Its surface is a frozen, static wasteland, heavily cratered and ancient, unlike the fractured, youthful terrain of Enceladus with its famous plumes. How could a moon that looks so dead possibly contain a liquid ocean? The answer may lie in a delicate balance of heat. Scientists theorize that Mimas's orbit around Saturn is not a perfect circle but a slight ellipse. This eccentric path subjects the moon to a constant, rhythmic squeeze from Saturn's gravity, a process known as tidal heating. This internal friction could generate just enough warmth to melt a layer of ice deep beneath the surface, creating a subsurface sea. The thick, rigid, icy shell above it would act as a perfect insulator, trapping the heat and hiding all evidence of the ocean's existence from view. The Herschel impact itself provides a crucial clue. The fact that Mimas did not shatter suggests that its interior is not uniformly rigid. A liquid layer would have absorbed some of the shock, acting as a buffer that allowed the moon to crack but not come completely apart. This idea turns our understanding of these icy worlds on its head. It suggests that a geologically quiet surface can be a mask concealing a dynamic, liquid heart. If a moon as seemingly inert as Mimas can harbor an ocean, then the potential for hidden seas across our solar system, and perhaps even the galaxy, is far greater than we ever dreamed. What other frozen, silent worlds are secretly alive with water, and what might that mean for the possibility of life flourishing in the dark? Saturn periodically unleashes a planetary-scale tantrum that makes even its most violent hurricane seem tranquil. Roughly every 20 to 30 years, a brilliant white spot erupts in its northern hemisphere, rapidly swelling into a storm so vast it completely encircles the entire planet. This is the Great White Spot, a recurring cataclysm that has been observed for over a century and a half. Each outbreak is a meteorological monster, a colossal convective event where warm gases from deep within the planet punch through the upper cloud deck, spreading out like a cosmic bruise that churns for months. The sheer energy required for such a global upheaval is staggering, dwarfing the total annual energy output of our entire human civilization. So what internal alarm clock tells this storm to wake up with such reliable timing, and what hidden furnace fuels its fury? The leading theory points to Saturn's seasons and a slow, cyclical buildup of energy. Unlike Earth, whose axis tilt gives us relatively mild seasonal changes, Saturn's dramatic lean creates profound and lengthy seasons, each lasting over 7 Earth years. For decades, the Northern Hemisphere endures a long, dark winter, its upper atmosphere steadily cooling and shedding its energy into space. Scientists suspect this allows a dense, stable layer of lighter gas like helium to form a thermal blanket high in the atmosphere. This layer traps immense heat rising from the planet's interior, building up a tremendous reservoir of potential energy beneath it. When Saturn's orbit finally brings the Northern Hemisphere back into full summer sunlight, the upper atmosphere begins to warm. This warming may destabilize that heavy blanket of gas, causing it to suddenly sink. The removal of this weight would be like popping a colossal cork, allowing the pent-up heat from below to explode upward in a violent, planet-wide outburst of convection. This seasonal model elegantly explains the periodic nature of the storms, but it is not a perfect fit. The timing is not always precise, and some models suggest the energy buildup should occur faster than the observed 30-year cycle. This discrepancy hints at a deeper, more complex process. The true trigger might involve a delicate interplay between seasonal sunlight and the internal churning of Saturn's fluid interior, where the slow, sloshing motions of liquid metallic hydrogen act as a hidden pump, priming the atmosphere for its next great eruption. The Great White Spot is more than just a storm. It is a planetary pressure valve, a rhythmic reminder that even a gas giant must occasionally scream to release the immense energy bottled within its depths. Deep within Saturn, a storm of a different kind is perpetually falling. It is a rain not of water, but of helium, a theoretical downpour that could solve one of the planet's most fundamental mysteries, its excessive heat. Saturn radiates nearly twice as much energy into space as it receives from the Sun. This internal furnace requires a powerful, continuous source of fuel, and the leading candidate is an exotic weather pattern occurring thousands of miles beneath the cloud tops. The theory suggests that deep inside Saturn, where pressures are millions of times greater than on Earth and temperatures soar to thousands of degrees, hydrogen is compressed into a bizarre, liquid metallic form. In this searing, electrically conductive sea, helium is thought to behave like a gas dissolved in a liquid. But as Saturn slowly cools over billions of years, the helium becomes less soluble. It begins to condense, forming into microscopic droplets. These droplets, being denser than the surrounding liquid metallic hydrogen, would then begin a long, slow, and permanent descent toward the planet's core. This is the helium rain hypothesis. Think of a bottle of chilled soda. When it is cold, the carbon dioxide gas is dissolved and invisible. But when you open the warm bottle, the gas suddenly becomes less soluble, forming bubbles that fizz and rise. Inside Saturn, the opposite is happening. The planet's gradual cooling is like opening the bottle, causing the helium to come out of solution and fizz downward as a fine, superheated mist. This constant gravitational settling of helium droplets releases an immense amount of potential energy, which is converted into heat as the droplets fall, frictionally heating the surrounding hydrogen. This process would act as a planet-wide engine, continuously stoking Saturn's internal fires and explaining its surprising warmth. Yet for all its elegant logic, this remains one of the most difficult ideas to prove. The pressures and temperatures required to create liquid metallic hydrogen and helium rain cannot be sustained in any laboratory on Earth for more than a fraction of a second. Our best evidence comes from complex computer simulations, which struggle to accurately model the intricate fluid dynamics and quantum mechanical effects at play in such an extreme environment. The helium rain remains a ghost in the machine, a beautiful solution to a planetary energy puzzle that we can only observe from its distant thermal consequences. If this internal drizzle is real, what other exotic forms of precipitation might be falling in the hidden hearts of other gas giants forever beyond our direct sight? But these internal storms are not the only light shows Saturn can produce. High above its poles, the planet paints the sky with auroras of breathtaking scale and complexity, displays that both mirror our own and defy all earthly logic. On our world, the northern and southern lights are a direct response to the solar wind, that stream of charged particles flowing from the sun. When these particles are channeled down our planet's magnetic field lines and collide with atmospheric gases, they create shimmering, dancing curtains of color. Saturn has its own version of this, but its auroras are a hybrid phenomenon, a confusing blend of solar and planetary influences that has left scientists puzzled. They are partly driven by the sun, yet they also pulse with a rhythm that seems tied to the planet's own deep rotation, a cadence we cannot even reliably measure. This dual nature creates a light show that is strangely independent, at times flickering in ways that have little to do with the sun's activity. The mystery deepens with the realization that Saturn's magnetic environment is not a closed system. The geysers of Enceladus are actively involved, constantly injecting a fresh supply of water vapor and ice particles into Saturn's magnetosphere. These particles become ionized, creating a heavy, cold plasma that is then spun outward by the planet's rapid rotation. This enriches and fundamentally alters the magnetic environment in which the auroras form, adding a third, internal driver to an already complex system. So you have a celestial light show being orchestrated by three different conductors at once: the solar wind, the planet's own spin, and the breath of a distant icy moon. Scientists are still trying to untangle how these forces compete and collaborate. Does the plasma from Enceladus dampen the auroras or make them brighter? How does the energy from the solar wind transfer into a system already so energized from within? The result is an auroral display that is not just beautiful, but a visible fingerprint of Saturn's deeply interconnected and mysterious magnetic personality, a luminous puzzle shining in the void. Far out from the brilliant rings, in the frigid darkness, a lone moon marches to a different beat. Phoebe orbits Saturn backwards, a rebel moving in the opposite direction of nearly every other moon in the system. This retrograde path is the first clue that Phoebe is a stranger, an interloper from the distant reaches of our solar system. Its dark, heavily cratered surface and unusual composition tell a story that does not belong here. While Saturn's inner moons are predominantly bright water ice, Phoebe is rich in carbon dioxide and complex, dark organic compounds. It looks and feels nothing like its neighbors, resembling instead the primordial objects found in the Kuiper belt, that vast cloud of icy remnants beyond Neptune. This profound mismatch suggests a dramatic past, that Phoebe was not born in place around Saturn, but was captured by the planet's immense gravity, snatched from its original home in the cold outer darkness. The mystery is how such a celestial kidnapping could have occurred. Capturing a moon is not a simple process. An object flying by on its own orbit does not naturally slow down enough to be caught. It would simply swing past and continue on its way. For Saturn to ensnare Phoebe, something had to act as a brake, robbing the moon of its orbital energy. One compelling theory involves a cosmic traffic jam in the early solar system. Billions of years ago, the space around the young giant planets was likely filled with countless small, icy bodies. Phoebe could have been one of them, and as it passed close to Saturn, it may have interacted gravitationally with one of Saturn's existing moons. This three-body gravitational dance could have provided the precise braking force needed, slowing Phoebe just enough for it to fall into a stable, albeit backward, orbit. Another possibility is that Phoebe was once part of a binary pair, two objects orbiting each other. As this pair approached Saturn, the planet's gravity could have torn them apart, capturing one while flinging the other away into interstellar space. This violent separation would have provided the energy exchange necessary for the capture. Phoebe, therefore, is more than just a moon, it is a captured time capsule. Its surface is a frozen record of conditions in the outer solar system over 4 billion years ago, a sample of the ancient building blocks that went into forming the giant planets. Studying its composition is like reading a page from the solar system's original recipe book, one that was never meant to be delivered this close to the Sun. Its very presence forces us to confront the chaotic, dynamic nature of planetary formation, a time when worlds were not yet settled in their paths and gravitational fortunes could change in an instant. What other secrets from the dawn of our solar system are locked within its dark, icy crust? And what does its successful capture tell us about the unseen population of wanderers that once drifted between the infant giants? Even the apparent emptiness around Saturn is an illusion of breathtaking complexity. Look closely at the dark bands separating the brilliant A and B rings, and you are witnessing a masterpiece of celestial mechanics. The Cassini division, that famous, seemingly empty gap, is not a void at all. It is a region meticulously cleared and maintained by an invisible gravitational hand, a force that reaches across 100,000 miles of space. The architect of this particular emptiness is Mimas, the Death Star moon. Its gravitational influence creates what scientists call a resonance. For every 2 orbits that a ring particle makes within the Cassini division, Mimas completes 1 orbit. This 2-to-1 rhythm is a cosmic drumbeat, and with every synchronized pass, Mimas gives that particle a consistent, tiny gravitational tug. Over millions of years, these repeated, rhythmic nudges are like pushing a child on a swing at just the right moment, each push adding more energy. The cumulative effect is powerful enough to eject the particles from the gap entirely, flinging them into new orbits and leaving behind a stark, clean division. The concept is elegant, but it leaves a subtle, lingering puzzle. This gravitational resonance is excellent at clearing out larger chunks of ice and rock, but what about the fine, dusty material? Why is the Cassini division so remarkably free of even the tiniest particles, the kind that should drift back in or be knocked loose by collisions? The gravitational forces from Mimas alone might not be strong enough to prevent this microscopic dust from settling back into the gap. This suggests that other, more subtle forces are also at play. Perhaps electrostatic levitation, similar to what creates the spokes, pushes this fine dust away, or maybe the faint pressure of sunlight itself helps to sweep the division clean. The precise mechanics of maintaining this pristine emptiness, of keeping a cosmic vacuum cleaner running so effectively, is a detail that scientists are still refining. This gap and others like it are not just empty space. They are a dynamic record of gravitational relationships, a visible demonstration of how a moon we can easily see can sculpt a region we mistakenly perceive as nothing. What other subtle forces are collaborating to maintain this perfect illusion of absence? And what does that tell us about the delicate, invisible web that holds the entire ring system together? This electrical personality extends far beyond the ghostly spokes. Saturn's rings themselves are not a passive collection of ice, but a dynamic, electrically charged structure. They are constantly bathed in a flow of charged particles from the Sun and immersed in the planet's own powerful magnetosphere. This environment strips electrons from the tiny ice particles, leaving the entire ring system with a positive charge, a phenomenon that fundamentally alters their behavior. It is as if the rings are plugged into a cosmic battery, and this current is rewriting the rules of their existence. This electrical charge creates a direct link to Saturn's upper atmosphere, its ionosphere. The charged ring particles and the ionosphere can exchange energy, creating a circuit that spans thousands of miles. This interaction might be responsible for draining away electrically charged material, contributing to the very ring rain that is slowly eroding the system. The rings are not just falling into Saturn, they are being pulled in by invisible electromagnetic forces as well. This charging process also dictates the fate of the tiniest particles. The fine, dusty material in the rings, which would normally clump together under gravity, is prevented from doing so by their mutual electrical repulsion. Like trying to force together the same poles of two powerful magnets, the similarly charged dust grains push each other apart, maintaining the fainter, dustier rings in a state of delicate suspension. This solves one puzzle while creating another. We now understand why certain rings remain so diffuse, but we cannot yet fully model the chaotic dance of charging and discharging that must be occurring every second across billions of individual particles. What is the precise trigger for an ice grain to gain or lose its charge, and how does this microscopic event ripple outward to shape the grand structure we see from afar? The entire ring system is a colossal, slow-motion electrical storm, and we are only just beginning to understand its silent, invisible lightning. That final, deliberate act of discovery may be the mission's most profound legacy. After 13 years of unveiling Saturn's secrets, the Cassini spacecraft was running out of fuel. Rather than risk an uncontrolled crash that could contaminate a pristine moon like Enceladus, mission controllers chose a spectacular and scientifically invaluable end. They sent the robotic explorer on a series of 22 daring dives, plunging through the narrow, unexplored gap between the planet and its innermost rings. This grand finale was a final, high-stakes gamble to taste the space where no probe had ever ventured. As Cassini threaded this cosmic needle, it measured Saturn's gravity and magnetic fields with unprecedented precision, sending back data until its final fiery moment in the planet's atmosphere. The readings held stunning surprises that are still reshaping our understanding of this gas giant. The planet's gravitational tug was not quite what models had predicted. The data revealed that the jet streams we see swirling in its atmosphere run thousands of miles deep, suggesting that Saturn's magnificent weather is not just a thin, superficial skin, but a fundamental expression of the planet's entire interior churn. This was a monumental shift in thinking. Even more startling were the precise measurements of the ring's mass, derived from the subtle pulls they exerted on the spacecraft during its close passes. The rings were confirmed to be even lighter than some estimates, a critical piece of evidence supporting the shocking theory that they are a young, temporary feature in our solar system. But the magnetic field data delivered the greatest puzzle of all. The field was even more perfectly symmetrical than anyone had imagined, with virtually no detectable tilt. This bizarre smoothness is what makes measuring Saturn's rotation so difficult, and it forced scientists to propose radical new ideas about the planet's deep interior. Some now suggest that a layer of helium rain falling through the liquid metallic hydrogen could be smearing and smoothing the magnetic field, effectively hiding the true spin of the solid core. Cassini's final sacrifice did not provide clean answers. Instead, it handed us a new set of deeper, more fundamental mysteries. Its last transmissions were a gift of profound questions, ensuring that long after the spacecraft was gone, Saturn would continue to challenge us from a billion miles away. From the permanent hexagon at its pole to the phantom spokes in its rings, Saturn has shown us a universe of enigmas. We have explored a world where rings rain into the atmosphere and may be a fleeting spectacle of cosmic youth, where one moon is two-faced and another hides a global ocean. We have encountered moons shaped like flying saucers, a moon that tumbles chaotically, and another that orbits backwards as a captured relic from the solar system's dawn. We have grappled with a planet whose day we cannot measure, whose interior drizzles helium, and which erupts in planet-wide storms on a 30-year timer. These 25 mysteries, from the warm polar vortex and the missing ammonia to the electrically charged rings and the shepherded chaos of the F-ring, all paint a single, compelling picture. Saturn is not a serene, finished world, but a dynamic and deeply mysterious giant, a place where the fundamental laws of physics are constantly being tested and rewritten. So, as the Cassini mission's final data continues to be analyzed, we are left to wonder, which of these profound secrets captures your imagination the most? Is it the possibility of life within Enceladus, the fleeting beauty of the rings, or the geometric perfection of that northern storm? Share your thoughts below and never stop looking up at the stars, for the next great discovery is always waiting just beyond the edge of our understanding.